Picture a 20-story skyscraper falling from the very edge of space. It's not a building made of concrete, but a 250-ton stainless steel monster known as the Super Heavy Booster, and it's plummeting back to Earth at supersonic speeds. Now ask yourself the impossible question: how do you catch a massive object traveling at Mach speeds without it detonating into a catastrophic, city-shaking fireball upon impact? The solution is a piece of radical engineering that defies every traditional law of aerospace retrieval. Welcome to Mechazilla. Standing nearly 500 feet tall, taller than the Great Pyramid of Giza, this launch and catch tower is equipped with specialized, massive mechanical arms known simply as the Chopsticks. These aren't your typical construction cranes, they are ultra-precise, high-strength appendages designed to track, intercept, and snatch a falling giant right out of the sky. As the booster screams back through the atmosphere, its Raptor engines relight in a violent, controlled explosion, fighting the crushing force of gravity to execute a perfect suicide burn. The margins for error are non-existent. A millisecond too late, and you have a skyscraper-sized kinetic bomb striking the launch site. A millisecond too early, and the booster drifts out of reach. This is, without a doubt, the most insane engineering gamble in the history of space flight. A moment where high-stakes physics meets pure imagination, turning science fiction into documented reality. But how does this towering machine actually calculate the intercept of a falling skyscraper in real time? To understand that, we have to look inside the brain of the Mechazilla. To understand why this is considered the most difficult maneuver in the history of flight, we have to look at the sheer scale of the physical forces at play. The Super Heavy Booster is a 232-foot tall tower of stainless steel. That is roughly the height of a 20-story building. When it begins its return trip from the edge of space, it isn't just drifting down like a leaf. It is a 250-ton kinetic projectile plummeting toward the Earth. As the booster re-enters the dense layers of the atmosphere, it is traveling at Mach 5. That's over 3,800 miles per hour. At these speeds, the air doesn't just flow around the rocket, it strikes it with the force of a sledgehammer. The friction generates a halo of superheated plasma that would incinerate almost any other vehicle. This is part one of the impossible task, surviving the descent while maintaining a precise trajectory toward a single point on the Texas coast. Imagine trying to catch a full-size school bus. Now, imagine that bus is falling from the summit of Mount Everest, and instead of a soft landing pad or a giant net, your only tool is a pair of giant mechanical chopsticks attached to a steel tower. The math behind this is staggering. The kinetic energy possessed by a 250-ton object moving at supersonic speeds is enough to level a small city. Every square inch of that stainless steel hull is under immense aerodynamic pressure, vibrating with the force of its own momentum. The risk factor here is absolute. In aerospace engineering, we often talk about margins of error, but for the Mechazilla Catch, those margins are virtually non-existent. We are talking about a window of just a few milliseconds. If the flight computer is off by even a fraction of a percent, the booster becomes a 20-story bomb. A slight gust of wind or a minor sensor glitch could send this massive structure slamming into the launch tower. The resulting explosion wouldn't just be a fire, it would be a multi-billion-dollar crater where Starbase used to be. Now, let's look at the execution, the dance of death as the booster nears its target. The sequence starts at an altitude of approximately 10 kilometers. The booster is still falling at incredible speeds, but it begins to use its grid fins. These 4 titanium meshes act like high-speed rudders. They rotate and tilt with surgical precision, using the rushing air to steer the massive rocket toward a 400-foot tall steel tower. It is a game of high-speed chess played against the atmosphere. As the booster reaches the final few thousand feet, the most critical phase begins. This is the relight. 3 or more Raptor engines must ignite simultaneously. These are the most complex methane-fueled engines ever flown, and they have to work perfectly the first time. There is no backup plan. As the engines roar to life, they perform a landing flip, pivoting the entire 232-foot structure from a horizontal fall to a vertical position in a matter of seconds. This leads us into the suicide burn. The name isn't hyperbole. It is a maneuver where the engines fire at the absolute last second to cancel out the rocket's downward velocity exactly as it reaches the height of the mechanical arms. If the engines fire too early, the rocket runs out of fuel and drops. If they fire too late, it slams into the tower. The physics require the velocity to reach zero at the exact moment the booster is in position. It has to be perfect. Inside the Starbase mission control, the tension is suffocating. This is a dimly lit room where the only sound is the hum of cooling fans and the steady, rhythmic callouts of flight controllers. They aren't looking out the windows at the rocket, they are staring at high-definition telemetry screens. They see the altitude dropping 5,000 feet, 2,000 feet, 500 feet. They are watching the error bars on their screens, hoping the blue line representing the booster's path stays perfectly centered. On the screens, the booster appears like a glowing needle on a digital map. You can see the Raptor engines gimbaling, tilting back and forth thousands of times per second to keep the rocket balanced on a pillar of blue flame. It looks impossible. A 20-story building is hovering inches away from a steel tower held up by nothing but burning liquid methane and raw computer processing power. For a few heart-stopping seconds, the booster is suspended in mid-air. It has successfully navigated the vacuum of space, the heat of re-entry, and the chaos of the lower atmosphere. It is now exactly where it needs to be, right between the open, waiting arms of the Mechazilla tower. But even as the booster hovers there, the most violent part of the mission is about to begin. How do those steel arms actually absorb the impact of a vibrating 250-ton rocket without snapping like toothpicks? How does a structure made of steel and hydraulics actually manage to snatch a falling giant without being ripped apart by the sheer kinetic energy? To understand the Mechazilla, you have to stop thinking of it as a tower and start seeing it as the world's largest, most precise robot. The Chopsticks, those massive mechanical arms, are the business end of this machine. They don't just sit there waiting to be hit, they are part of a high-speed, closed-loop feedback system that is constantly adjusting to the rocket's position. The secret lies in the tower's backbone, a series of ultra-heavy-duty tracks and a hydraulic carriage system that moves the arms vertically and horizontally with surgical precision. But how does it know exactly where the booster is at every millisecond? Think back to how a Hellfire missile uses semi-active laser homing or millimeter wave radar to track a moving boat. The Mechazilla uses a similar logic, but at a much larger scale. It employs a suite of real-time LiDAR sensors and high-speed computer vision cameras that create a 3D digital twin of the descending booster in the tower's brain. This allows the system to calculate the booster's drift, tilt, and velocity, moving the arms to the perfect intercept point before the rocket even arrives. Now look at the booster itself. You can't just grab a rocket anywhere. The hull is made of thin stainless steel. If you squeeze it in the wrong place, it crumbles like a soda can. This is where the load-bearing pins come in. These are massive, reinforced hardpoints protruding from the side of the booster. They are the only points on the entire 250-ton structure designed to handle the full force of a catch. The Chopsticks are equipped with specialized catch rails that slide under these pins. It's a game of inches. The arms must be open just wide enough to let the booster descend through them, then move in with lightning speed to secure the pins as the engines shut down. But what about the impact? When a 250-ton object, even one hovering, settles onto a fixed structure, the shock waves could be devastating. This is solved through an advanced shock absorption and damping system. The arms are designed with compliance, a fancy engineering term for a controlled amount of give. As the pins make contact, hydraulic dampers within the carriage act like a massive car suspension, absorbing the remaining kinetic energy and bleeding it off safely into the tower's foundation. Compared to a standard construction crane, which is designed to lift steady loads, the Mechazilla is built to catch a vibrating, heat-stressed, and unpredictable beast. It is the difference between picking up a suitcase and catching a falling refrigerator while standing on a ladder. Behind this wall of steel and fire, there is an invisible layer that is just as critical: the data. For a catch like this to work, thousands of sensors must talk to each other at sub-millisecond speeds. Any latency, any lag, or any interference could lead to a catastrophic collision. In the world of high-stakes aerospace, data security is just as important as the physical armor on the tower. Just as a military drone requires a secure, encrypted link to operate in hostile territory, the Starship launch system relies on a fortress of information. Protecting these command centers from bad actors, malware, or signal interference is a 24/7 mission. One harmful download link or one compromised server could jeopardize years of engineering and billions of dollars in hardware. It's why robust defense mechanisms are built into every level of the network, ensuring that the only thing controlling those chopsticks is the precise logic of the flight computer. So, why go through all this trouble? Why build a giant robot tower to catch a rocket instead of just using landing legs like the Falcon 9? The answer is the strategic big picture. When you look at traditional rockets, they are essentially disposable. Imagine flying a Boeing 747 from New York to London and then set it on fire and throwing it in the ocean as soon as the passengers get off. That is how we've been going to space for 60 years. It's why space travel has always been the exclusive playground of superpowers and billionaires. By removing the landing legs from the booster and putting the landing gear on the tower, SpaceX has pulled off a masterstroke of weight reduction. Landing legs are heavy, they require hydraulics, structural reinforcement, and fuel to carry them all the way to space and back. By leaving them on the ground, the Starship can carry significantly more cargo, or more people. This is the key to reusability. The goal isn't just to save the rocket, it's to turn it around and fly it again in hours, not months. This shifts the entire economic landscape of humanity. Currently, it costs thousands of dollars to send a single kilogram of material into orbit. With a fully reusable Starship caught by Mechazilla, that cost could drop to less than $100. We are talking about moving from a world where space is a rare destination to a world where orbit is a high-frequency logistics hub. Picture a future harbor, but instead of ships carrying containers across the Atlantic, you have a fleet of starships being caught by dozens of towers around the globe. This is the Mars Highway. To build a self-sustaining city on another planet, you don't need one or two successful launches, you need thousands. You need a pipeline of fuel, food, and building materials moving constantly. The Mechazilla Tower is the gateway to that pipeline. When you compare this to the space programs of the past, or even other nations today, the scale is overwhelming. While others are still struggling with disposable boosters, the US is perfecting a system that treats a 20-story rocket like a commercial airliner. It is a total pivot in how we perceive our place in the solar system. It moves us from being a species that visits space to a species that lives in space. This isn't just about a cool engineering trick in South Texas, it is about the long-term survival of the human race. By mastering the catch, we have mastered the ability to leave our cradle and become a multi-planetary civilization. As we look at the tower standing tall against the horizon, it's a reminder that what once seemed like an impossible dream is now a matter of calculated physics and relentless ambition. But what does this mean for the next decade of exploration? And how soon will we see the first fleet of these ships heading for the Red Planet? In the end, what we are witnessing isn't just a spectacular sight on a Texas horizon. It is a masterpiece of modern physics. On one side, you have a massive, 20-story stainless steel skyscraper falling from the edge of space at supersonic speeds, a 250-ton kinetic projectile vibrating with enough energy to shake the coast. And on the other, you have the cold, silent calculation of a machine designed to intercept it. Through a perfect symphony of real-time telemetry, Raptor engine precision, and those massive hydraulic arms, the sheer violence of re-entry is transformed into a landing as gentle as a feather. This is the ultimate proof that the impossible is simply an engineering problem that hasn't been solved yet. By mastering the catch, we have built the first true gateway to the stars. We are no longer limited by the high cost of disposable rockets or the dead weight of landing legs. We are now a species that can launch, catch, and fly again within the same window of time. It is a total pivot in the history of human exploration. If you are fascinated by the raw power of these massive machines and the engineering that is literally shaping the future of our species, you belong here. We break down the world's most advanced technology to show you how the future is being built. Hit that subscribe button and turn on the notification bell so you don't miss our next exclusive technical analysis. The road to Mars is being paved right now, and we are tracking every single milestone. Thanks for watching, and we'll see you at the next launch.